So, as I said, this one is about large dimension infrared sensors for space and science application. And this is an overview, a summary of all the technical development we did. And Bruno Fieck will, right after, present the applications we can access with this type of sensors. So, I told you you would see it again. Here it is. So again, this is this type of technology here that we are talking about with photodetectors, photodiodes, on a readout integrated circuit. Here, the wavelength range for science and space application is different. We are not anymore in the MUIR region like I presented just before. We are in between up to 2.3 micron here, so in this range here. This is a case where we basically do a lot. When I said yesterday we do more than ST, this is one case like this. So we start with growing monocrystals of CD cadmium zinc telluride here. We cut them into wafers, polish them. We do epitaxy on them. We process photodiodes on them. On the other side, we have the same CMOS technology here. So we do the design, the ROIC design. We do post-process on CMOS wafers to be able to do the flip chip bonding, so connecting every single photodiode on one side to the ROIC circuit. And then after that, we do the packaging. It's a little bit different from the other case. Here it's for space application, for very different type of mission. So it can be either without integrated cooler, because, for example, it's provided by the satellite manufacturer, or it can be with a cooling system like this one. So the sensor we're talking about is very large dimensions. It's more than 2000 by 2000, 2048 by 2048 exactly. That's the number of pixels. Pixel pitch is 15 micron. And it has to be, so it's for space observation and astronomy, it has to be very, very high performance. Because if you sense a sensor in space on a satellite, it has to perform the best that you can do. So first, dimension is very, very big. It's more than 3 centimeters by 3 centimeters, so that's quite unusual. Dark current needs to be very, very low because we look at very small signals with this type of application. So basically less than 0.1 electron per pixel per second. That's the noise that we have to achieve. Readout noise also needs to be very, very low. So it's all in the design of the ROIC that happened, and obviously in the CMOS process. And quantum efficiency, we want to collect all the light that's available, or most of it, and so it has to be more than 75%. So the approach we had basically is to go very low TRL and develop everything the best that we can. So we even do ab initio calculations to look at defects, their impact on the performance of the semiconductor, atomistic characterization. We do TCAD, so computer-assisted design for the process itself, to understand how changing process parameter change the performance of the chip, electrical characterization, obviously, and electro-optical characterization as well. First, now I'm going to show you just a sample of technology breakthrough that we had to do for this product. I won't show you everything, but one first thing is the ROIC. ROIC dimensions, It's more than 3 centimeters by 3 centimeters. It's quite unusual for CMOS chips. So we had to work with the foundry to develop a stitching process to be able to do this type of large dimension ROICs. And we had as well to develop ourselves the right process for post-process on these wafers to be able to deposit indium balls and do the flip chip bonding. This is the dimension, the typical dimension of a sensor that's used for defense or civil application. It's a VGA format, 15 micron pitch. And right next to it is the dimension of this, the sensor we developed for science and space application. You see the difference in size. It's huge. So we couldn't use anymore the same type of dimension for the wafers. We had to develop crystal growth of larger dimension wafers. And so now, well, the standard was roughly 5 by 5, and now we have 4-inch wafers available for this type of product. And we do this in close collaboration with the CA-Leyte. This is a part where there is a need for collaboration with the RTO. I told you that performance needs to be extreme, so every defect in the crystal is potentially defect that you will find in the performance. It will be noise, it will be a pixel that doesn't work well, that doesn't have the right sensitivity. So we worked on that as well. And here we optimize so the dislocation density, the other phase in the crystal, tellurium rich or cadmium rich, to be able to attain this type of performance. So this is before we optimize the process. All these bits are emerging dislocation that you reveal after chemical etch. And that's what we got after process optimization. We also worked on the PN technology, on the diode technology. Our legacy technology, N-on-P. So this is just going back. This is the dark current density as a function of reverse temperature. So the lower we are here on this curve, the best is the performance. This is the legacy technology, and this is the technology that we have now. So we reduce by 2 orders of magnitude the dark current for the same wavelength, same temperature. One more challenge that we had to face is flip chip bonding of such big dimension components. 3 by 3 centimeters ROIC, 3 by 3 centimeters detection layer. So I think we have, yes. So we had to work on optimizing a lot of things from the part that holds the two components before we put them together, flatness of every single piece, the RIC and the detection component. We had to model exactly what the behavior with changing temperature of the two parts, because it's not at room temperature that this bonding happens. The indium bump deposition also has to be improved, process parameters, obviously, and equipment capability. And so that's a quick view of this. On the left, it's 10 micron indium bumps on the ROIC that allowed us to do the flip chip bonding of 2K square. No, that's not a 10 micron pitch FPA, that's a 15 micron pitch FPA. And this is how it looks in the package detector. And defectivity of this is less than 0.04%. And so last year we delivered prototype to ESA, and it will be used. It will be used first characterized and potentially used in satellites. And Bruno will show you now what type of application are possible with this type of device. Thank you.
You know, with people like you, timekeepers are useless. But we have plenty of time for a question.
Okay.
Yes.
Yeah, that was good.
Hold on a second. I will bring the microphone to you. Please just tell the audience who you are.
My name is Matthias. I'm a student from Lund University. I don't think I quite followed why it would be difficult to make the wafers larger. It feels like in nanoscience it's always about pushing the limits to the smaller sizes.
Why is it difficult to make crystals larger?
Yes.
Because it's a very high temperature process. Basically, we have a liquid bath of CdZnT, so cadmium zinc telluride. Then we have to very, very slowly apply a temperature gradient so that the top crystallizes and it propagates through the whole thing. And it happens at more than 1,000 temperatures. So here, the oven, the furnace development, the design, everything is critical to have the right condition and to have the homogeneity. So when we increase the dimension of the crystal, it becomes very difficult to control.
Thank you. One more question? So you see the students here in Lund are very sharp people.
Mm-hmm.
You can always count on Magnus when it comes to questions.
Hi, my name is Magnus Ride again. Would this process work in a large area fab better? Like the display fabs, you know, that do, because you're going to have a yield problem on the small, obviously.
Yes.
And if you go to a larger substrate, you know, your yield averaging becomes much better, presumably, if you can control the surface area, right?
Absolutely. And that's why yesterday I talked a little bit about the infrared campus project that we have to expand our clean room surface. And in addition to being more surface of clean room, it will be higher standard clean room, state-of-the-art clean room, so that to be able to have lower particles defect and higher yield on this type of process.
Yeah, but do you plan to go to a larger substrate, like a glass substrate, you know, that kind of thing?
No. The volume is not large enough for that type of investment.
Here we have Bo Hammarlund from Epiluvac.
Well, I have one question for you here. I mean, if you compare indium gallium arsenide and image processing, could you come close as the quality as you have now, or?
In terms of?
Well, in terms of cost for the buyer and image quality. What is the special here? I mean, you need cooling and you need
image quality. I think it's on par with InGaAs, for example, because I showed 0.04% defectivity on a 2000 by 2000. It's very, very low. We have very good uniformity, very low noise. So I think we're on par with the others.
Yeah. All right. Yeah. Thanks.
Thank you. One more question, the last one.
Why not?
Anyone? Because you seem to be awake now. Yes? Good. Okay. Thank you very much for your questions.
Thank you, Patrick.